Log on, tune in, find out. Another good idea from Cambridge.
My pleasure to introduce the next speaker, Takeshi Suzuki from Okayama, who will talk about conformal field theory and Cherednik algebra.
Thank you. So I'd like to thank the organizers for giving this opportunity. Today, I'd like to talk about conformal field theory and representation theory of Cherednik algebra, and also other algebras. So conformal field theory is a model of field theory and has been developed both by physicists and mathematicians for 30 years. In mathematical formulation of conformal field theory, the representation theory plays an essential role, and also several results in representation theory have been applied to this physical model. But this talk concerns, in a sense, opposite direction. So I will talk about contribution of conformal field theory to representation theory. So I will talk how could conformal field theory become an origin in physics in my study of representation theory. So the first, Cherednik homological functor in conformal field theory. So first of all, so what is conformal field theory? I don't know the definition of conformal field theory, and we don't need to know in this talk. So we don't need to know the whole picture of conformal field theory. So for our purpose, we just need to recognize it as a recipe presented by physicists, which gives a way to construct vector bundle starting from representation of some algebras. In my talk, the representation of Lie algebras. So you input several representations of Lie algebra, affine Lie algebra. Then a recipe gives you some vector bundle on some configuration space. I denote by X, configuration space of points in general on Riemann surface, but we just concern CFT on P1, so configuration space of points on P1 with integrable connection. So then you have several modules of affine Lie algebra, and then one gets vector bundle on configuration space, which I specify explicitly, and plus some connection. And the vector bundle is called, I call this vector bundle the vector bundle of conformal coinvariant. And this connection is called Cherednik topological connection. So anyway, so you have some vector bundle with connection. So one can consider monodromy representation. So arrows from here. We have then one gets representation of fundamental group of configuration space. So in this sense, conformal field theory is a functor which relates category of representations of Lie algebra and category of vector bundle, category of representation of group. And so the basic problem here is to study conformal field theory as a theory of functors. So actually, this picture is still too general. So we need to find a special and significant setting. And the purpose of this talk is to give an example of such a nice setting, where we will see that conformal field theory connects Lie and Cherednik and Hecke algebras. I mean, in type A. So, so Lie algebra appears here as an algebra of the symmetry of the model. And the Cherednik algebra, which has been appeared in several talks, related to algebra of differential operators. So it is related to here some connection, KZ connection. And Hecke algebra appear via monodromy. So I will show what is a connection, what is a functor, concretely, and how nice they are. Actually, some of these functors are nice and mathematically new. So, okay. So first, let's introduce several notations on affine Lie algebra. Okay. So we just treat type A GLN, AM GLN. So it has a basis consisting of matrix unit Eij, and G hat is an associated affine Lie algebra, and C denotes the center, and it admits triangular decomposition. So here G plus minus is a positive and negative power part. And for kappa, non-zero number, we define category of J-hat module. That is a category of highest weight module of level kappa minus m. So level kappa minus m means that C acts as a scalar kappa minus m. So in other words, kappa is a level plus dual Coxeter number. And highest weight module means highest weight module with respect to this triangular decomposition. So in particular, this is G plus locally nilpotent. And also we prepare lowest version. So we have minus level. Okay. So typical object of the category is a Y module, and the definition is this here. Okay. So we will see a little bit more precisely. So conformal field theory on Bess, Zuminov, Novikov, written model on P1 with n plus 1 point. The reason why I denote n plus 1 is that we have n moving point and one fixed point, namely fixed at infinity. So the picture is n moving point. So we have n plus 1 point on P1, but 1 point is fixed at infinity. So other n points are moving. And it means that we consider the following configuration space. X is a C to n minus some diagonal set. Okay. So here, of course, we identify P1 minus infinity with C. So if we choose n plus 1 point, so we denote m1 to mn and m infinity from O kappa G hat, then CFT gives the vector bundle of conformal co-invariant and connection on it. So I will not explain. I prepared some, but I have no time to explain what is vector bundle in general and what is connection, KZ. So I skip the precise definition of them. But if you want to know that is here. But it is not essential in this talk. I will see in more special setting, I will see more explicit realization of conformal co-invariant. So we make special choice. Of modules. So namely, we take M1, M2, Mn are all equal to B hat kappa. And here, B is a basic representation of G, so G. And B hat is a while module associated to this irreducible module. So highest weight while module. And so we have a special choice, but we have still one freedom of choice. So we can choose M from G hat or kappa freely. So okay, so for some reason I take from lowest weight modules, and then proportion. As I said, the vector bundle of conformal co-invariant under this special choice. I will explain about M check is described as follows. So I will explain some notation. So first of all, so M check is okay. So this is not important. So M check is some functor, duality functor. So it's from O minus to O. So minus to plus, or plus to minus. So given by some algebra involution, Lie algebra involution of G hat. So I will not give a precise formula for this. Sorry, but anyway, so and
Between the last line, it is M or M check?
this is M.
I'm sorry,
Yeah.
it is lowest. So you take the total several highest weight modules and the lowest.
Yeah. Yes, yes. So, this is, I will explain this. So V is finite dimensional module, and this is loop module. So, yeah. Okay, here. So, what is, oh, sorry. And I, this is, as a space, this is just this. And so GT acts on this space naturally. So T is Xi on this space. Okay. So we have N GT module, and also this is G hat module. So by restriction, this is also GT module. So we have a tensor product of N plus 1 GT module and take co-invariant. So and our notation, this is okay. So, and also I should mention that. So I used sheaf module correspondence. So the category of case coherent sheaves on X is equivalent to the category of module over coordinate ring of the affine variety X. Okay. So under this correspondence, so vector bundle or locally free sheaf correspond to projective module over this, and so we describe this as a module. So this isomorphism is as CX module. So this follows from standard argument from in conformal field theory. Okay. So for later use, we put F M as this co-invariant space. So okay. Then this is as a space or as a module over over polynomial ring. This is isomorphic to yes. So in particular, this is a module over this polynomial ring. So this is also a coordinate ring of this bigger affine variety. So this is a sheaf over this bigger variety, and if you restrict that sheaf on this subvariety, then you get vector bundle or sheaf of conformal coinvariant. This is the statement. So this is a description of the vector bundle of conformal co-invariant under our special selection of module, and also one get KZ connection. So okay, again, I don't have time to even explain about explicit formula, but that is here. And so anyway, the point is that so there exist some operators on this vector bundle or this module. So V hat, V hat, and check. Okay. Which is given by explicit formula using an element of affine Lie algebra, and it satisfies zero. And also, so since this is an expression of integral connection in vector bundle, so it satisfies this equality. And also, moreover, we have this is SN equivariant. Okay. here, Sn denotes a symmetric group. And this acts on this vector band. Okay, so you see in this expression, the symmetric group acts as a permutation of variables and also a place of component of tensor product. So this is
in KZ connection. Are you supposed to divide omega I by xi? Isn't it supposed to be with regular singularities?
yes,
So then you have to write omega I over xi. No.
no.
So what's the meaning of omega I? Usually,
Then it will not have regular singularity at infinity.
isn't KC usually without omega I?
P is bigger than 1. P is bigger than 0.
P.
In the definition of omega, okay, P is here.
Ah.
One.
Okay. Yeah, I understand.
Can I ask, usual definition of KC is without omega I.
Right.
What does it mean?
So, yeah,
We haven't taken the coinvariance in the last factor somehow. Yes. And that's why we still have elements of affine out here.
yes.
If a last factor is also induced, then you can rewrite it, like I said, with something divided by
So okay, then I will not explain. Okay, so starting from some representation of the hat, we constructed vector bundle. It's here, and also with connection, and the connection is Sn equivariant. So we have obtained Sn equivariant vector bundle, or in particular, we obtained a module of this algebra. So here, diff x is an algebra of algebraic differential operators on x, and that symmetric product with n. So recall that this is just a coordinate ring part, and so this is simple algebra. And then, as I said before, we take monodromy.
Madam, how do you, if you have low weight module, you say you associate a module over this?
Yes. This admits an action of Sn, and also this admits an action of coordinate ring, and also the action of this differential operator is given by this connection. Yeah. So, okay. So then, taking monodromy, we have a representation of a fundamental group of the affine variety, but now we have SN equivariant bundle, so we get the action of the fundamental group of X over symmetrical group. And as is well known, this is a break group, Artin's break group on complex plane. So the well-known fact about this action. So okay, so let me denote this functor. So obtained by composition of the operator functor. So denote by k, z for g hat. So this is a kg functor in conformal field theory, or kg functor for the affinity algebra g hat. So fact is that the image of kz is in HQ mode. This is some subcategory of this module category, and here HQ is Hecke algebra. So that is a quotient of this group algebra of the break group by so here Bi is a standard generator of Bn, and Q is exponential kappa 2 pi with minus 1. Okay. So in particular, if kappa is a rational number, then you have a root of unity as a parameter. So it's natural to ask how good is this functor from the category of G hat, the category of HQ mode. But before considering this problem, we proceed to Cherednik. Stop. So we have found two algebras, Lie affinity algebras and Hecke algebras. And where is Cherednik? Here. Okay. So recall the definition of the rational Cherednik algebra of the symmetric group. This I define as a subalgebra of this algebra generated by the following elements. So here, Di is the Dunkel operator. here, Sij is a permutation of I and j. So probably this Dunkel operator is different from standard Dunkel operator because we, yeah, so, okay, so standard Dunkel operator had 1 here, but this is also gives an embedding of this algebra into this algebra. And also, we have this important property. Okay. So,
If you don't have the 1 there, can you get rid of the denominator?
sorry?
The 1 is usually useful to get rid of the denominator, xi minus xj.
Yeah.
You mean 1 minus s rather
Yes.
than
Yeah.
Well, we don't really care whether it maps polynomials to itself.
Right.
It's correct, right?
Right.
Why not?
I mean, it's easy to add. This is conjugate to the usual one by the conjugated by the product of xi minus. To the power. 1 minus.
So, then we have another KZ functor. That is, so you start from some highest weight module of H kappa. So this is some the category of some highest weight category of H kappa module, which has been appeared in Gordon talk. I will omit the definition. Sorry. So, and then take localization. But then you have the module of this. Okay. So for n, you consider over polynomial ring, and then you get the module over this by this isomorphism, and then take monodromy. So localization and monodromy, and so again you obtain module of a braid group, and the same fact happen for Cherednik algebra, namely, so KZ for H. So by this I mean the composition of these two functors. It gives the functor from category O to the category of Q. Okay. And moreover, it has to be shown that this gives induce some categorical equivalence between the quotient category of this and the module category of Hecke algebra, as shown by Ginsburg, Guy, Opdam, and Lukier. So, So we have two KZs. Okay. So this is from conformal field theory. One is from Cherednik algebra. This is localization. This is some conformal co-invariant construction. And then take monodromy. Then a priori, this is a functor in this category, but actually the composition, image of the composition goes inside the full subcategory of Hecke algebra modules. And recall that, so for M, the image of here is given by I have by this one. So image of this was some of this form F M. So on the other hand, the functor here was a localization. So and the good thing about here is theorem. It's so H kappa preserves F M. Okay. So this space is a module over this algebra of differential operators. So here, dxi acts as a KZ connection, number I, but this number I doesn't preserve Fm because it has a pole at xi equals xj. It acts only after localization, but there is an element, Dunkel operators here. So that di that preserves Fm. This is what I mean. So one gets the functor a priori this is H kappa module. And moreover, it's not difficult to show that this is inside, the image is in category O. So we have two KZs. With the same target categories, and their relation is obtained by this F. So this commutes. So the problem.
Does that mean you can somehow classify the O category for the Hecke algebra, for the Cherednik algebra, by the O category for the G-hack module?
Classification of simple module.
I mean, does this F allow you to classify the modules in the O category for the Cherednik algebra using the modules for the category for the G hat?
Yes, in a sense, but yeah. Yeah, I will explain about that point. So how good is this f? Okay. Or how good this function? So this is good. By GGOR.
What does it mean?
Good. I don't know. For example, exact. Yes, yeah.
So it's a quotient by a third subcategory. This means
Yeah, that is very good. Okay, so first, the case kappa generic. So then, these categories become semi-simple. So, and it's so this is more or less the same with the module of finite G and module category of the symmetry group. So the functor is given by induction. Okay. So the
GSLN?
GLM.
Okay.
And so the function is in this realization is more or less sure. And so this is good functor in some sense. So how about general case?
Do you regard G as a Levy factor of G hat? Induction means you regard G as a Levy factor of G hat there.
Induction means
No.
and some it isn't embedding more precisely.
And the right-hand side is just similar. I mean, you extend sigma n module to two-thirds of the Cherednik algebra trivially, and then you induce. Is it the same idea? So induction on the right hand. Maybe write out what induction on the right hand.
Yeah, right hand.
Yeah.
It's a
So that's those are the x's or the.
so di Dunkel operator. So di act trivial.
And that diagram commutes somehow.
Yes. So how about more general case? So it's not it's easy to see that f is right exact. And also f sends wire module to standard module.
You mean standard model is model like this, right?
Yeah, yes, exactly. And but probably f is not exact on the whole category. To get nice category, nice functor, we need to consider restriction to the smaller category. That is, okay. So for simplicity, let me specialize m equals n, and also, so m is the rank of G, and n is the rank of Cherednik algebra. So the O minus, and so consider full subcategory of O kappa minus such that whose Jordan-Haider component has always lowest weight corresponding to the partition of n. So I mean, so I'm identifying the Carlton with Cn, and so this makes sense. Then
Sorry, how good? What is M?
M was rank of G, GLM, GLM and HN. Yeah. And my conjecture, now it's theorem. Yeah. Was the following. So, if kappa is not positive rational number, then f restricts to an equivalence of abelian categories. So moreover, this makes the diagram commute. So, okay, so let me make some remark.
You said that H, it is HN, but then you're writing HK.
H kappa. Kappa is
Kappa is parameter.
yeah.
N.
H kappa of Sn and Nt.
Yeah. SN.
So remark that concerning this conjecture, so the categorical equivalence between O prime and OH is obvious. I mean, what is not obvious is that F gives an equivalence. And what I mean, so this O prime was a full subcategory of the lowest weight modules of G hat. And this category is, by Kazan-Lustig, equivalent to the module category of quantized enveloping algebra of G. And inside this, there is
that G or G hat?
G, finite G. So highest weight module or lowest weight modules of G hat and finite dimensional modules of G, UQG. That is a result by Kazan and Lustig. And inside this, there exist modules, categories of Q-sure algebras, because this is defined as a quotient algebra of UQG. And the category O prime I defined is a Q-sure counterpart of this affine real algebra side via Kazan-Lustig correspondence. And so we have this equivalence, and also Q-sure algebra was proved to be equivalent to the category O for rational Cherednik algebra by Lukier using the argument of K-psi hereditary covering. So this means that this and this are equivalent as a category. But as I said before, this is not obvious that F is not. F gives this equivalence. So, yeah. So.
By the way, is it important that you are on P1 on C, or you can take any curve and define similar things?
Yeah, I don't know.
I think so.
Yeah.
Some time ago, I defined the Cherednik algebras for curves, and I think it works exactly the same way, right? Because I mean, there won't be Dankel operators, but this is not the particular explicit form of them is not very important.
So maybe, yeah, we can expect something.
Yes.
Yeah, I have not tried. So I discussed with Raphael Lukier when I visited Oxford, and he noticed that this conjecture can be proved by using some abstract lemma concerning highest weight covering. But this proof is, in his words, not very good proof, because this proof needs both Kazan-Lustig and Lukier's equivalent. So this needs two deep results. So we expect more direct proof. Recent preprint by Baraniero-Bassero also introduced about Lukier's idea. Okay. So the final, let me make comment on some generalization. So we start from conformal field theory on P1 with n plus 1 point, but we can start with n plus 2 point, and 2 means 0 and infinity. So then, in this case, we have two choices of modules. So we have bifunctor, so the highest weight module and the lowest weight module. And then Cherednik counterpart in this situation is trigonometric Cherednik algebra or degenerate double affine Hecke algebra. This was done by Arakawa and me and Tsuchiya, 1998. And the Hecke counterpart is affine Hecke algebra, because the fundamental group of this configuration space gives a affine braid group, and affine Hecke algebra appears as a quotient of this affine braid group. And I don't know if this F tilde in trigonometric setting is good functor or not. Maybe not. But even for generic kappa, so for generic kappa in rational setting, it was in a sense trivial, sure why. So, but even for generic kappa, this functor was new and it turned out that this functor in generic gave a nice correspondence between the category of highest weight module of finite G. So this is, in some sense, inside this affine category between OG and the finite dimensional modules of degenerate affine algebra. So by using, for example, by using this functor, we could show that to obtain decomposition matrix for G for any rank, and to obtain decomposition matrix for H affine for any rank is completely equivalent problem. And so also another generalization so is done by Baragno-Barcelo recently. So here where they replaced rational Cherednik algebra for symmetric group by the rational Cherednik group algebra associated to complex reflection group using, and the functor is obtained via what is called O before the conformal field theory. And also another appearance of Cherednik algebra or double affine algebra in conformal field theory is pointed out by Ettinghoff, right? So, but the relation with this picture is not very clear so far.
So probably if you have any curve with a finite group, then you can attach such functor for it.
Okay, I stop.
Let's think. Any questions? Okay, so let's thank the speaker again and start new second talk in 2 minutes.